Welcome to my YouTube channel. Today I will be discussing an economical, basic, and custom security circuit with a schematic while comparing it to a commercial security system, then demoing a breadboard prototype and briefly discussing an alternative using an Arduino. I will first discuss my design considerations of either software and hardware or hardware only. Since I am mostly a software engineer, the easier task for me is software when coding logic and uploading to an existing chipset that includes a microcontroller, oscillator, and a UART chip. This combo can be found on an Arduino board. With this method, the only other component I would need is a MOSFET transistor to convert the low power of the Arduino to higher power for the horn. I would then solder the Arduino and MOSFET on a breadboard circuit. The horn I am using is inexpensive. It's actually a siren horn that draws 15 watts of power at 12 volts. This is 1.25 amps. And the noise it produces is 110 decibels. This is as much as a 20,000 seat arena cheering after a goal, or 75,000 people in an outdoor stadium cheering for a goal or touchdown. The siren horn sounds like police cars, and it's loud enough for the neighbors to hear it. With the auto reset timing circuit, it will turn off after 5-10 minutes, however long that I decide to configure the final circuit. And it's long enough for the neighbors to hear it and give me a call to let me know there's a possible intruder. It does not sound for an extended period of time to where the neighbors start becoming annoyed. Regarding the software and hardware design, if anyone is interested in coding, they can see some of my algorithms at this GitHub URL. I just have a few more thoughts on the Arduino before I get to the hardware-only circuit. As you can see, I did some experimenting with the Arduino. The board with the diodes is Project 2 from the Arduino project book, where coding can sequentially flash late-emitting diodes. The board with the speaker is Project 7 from the Arduino project book, where the buttons simulate piano keys, while the code deciphers a range of resistor values in a resistance ladder from analog input, and then digitally outputs varying tones on the speaker. I will now discuss the hardware-only circuit. The hardware-only circuit has dual voltage inputs, 5 volt and 12 volt. The circuit includes 2 inverters, SR latch IC, short for integrated circuit, 555 timer IC, comparator IC, RC circuit voltage divider, and a MOSFET transistor for the siren horn. Since the horn circuit is the simplest part of this security circuit, and since some of the information learned in this circuit can be used to help explain the differences in other circuits, I will start with the horn circuit. Unlike the 5 volt main circuit, the horn circuit is on a 12 volt circuit. Since the horn can operate on 12 volts, there is no need for a voltage drop resistor. Just like an incandescent light bulb in your house, or changing an incandescent light bulb on your vehicle, if a bulb or device is rated at the same voltage and the circuit can handle the wattage, there is no need for a voltage drop resistor. The switch in a 12 volt circuit is a manual switch intended to bypass the horn for if and when needed. The manual switch is rated for at least 12 volts and can handle more amperage than the horn uses. The transistor in the circuit is called a MOSFET transistor and is what is used between the 5 volt circuit and 12 volt circuit. The MOSFET transistor only needs applied voltage at the base, although there is a need to be careful of the heat a MOSFET can generate. There is a calculation to determine if a heat sink is needed, and this usually applies when exceeding more than half of a MOSFET's rated watts. For the small 15-watt 1.25 amp horn I am using, and the light-duty time cycle in the 5-volt circuit, the 60-watt MOSFET I chose does not need a heatsink. Regarding the LED circuit, a typical LED is rated between 2 and 3 volts, while requiring a voltage drop resistor in a 5-volt circuit. While a 220 ohm resistor is commonly found in a LED circuit with a 5-volt supply, the 220 ohm resistor is actually more than required. A definitive resistor value will require calculation using Ohm's law. In this picture, the V represents voltage, the I represents current, and the R represents resistance. And so the voltage divided by the current equals the resistance. And the voltage divided by the resistance equals the current. While the current multiplied by the resistance equals the voltage. There is one other calculation that is not pictured, and that is the wattage. And for the wattage, it's simply voltage times amperage equals wattage. For the calculations and the practical tests that I'll be explaining, the supply voltage is 5 volt, and the LED that I'll be using is 3 volt, drawing 20 milliamps. In the first calculation, we must calculate the voltage drop. The supply voltage is 5 volts, and then we subtract the voltage used by the LED, which is 3 volts, and that gives us a voltage drop of 2 volts. And then what we need to do is we need to convert the milliamps to amps for the calculations. So that's 20 milliamps divided by 1,000 is 0.02 amps. Then we must calculate the resistance. And with the resistance, what we have is the 2 volt voltage drop divided by the amperage used by the LED at 0.02 amps, multiplied by a safe factor. The end result is the resistor is 150 ohms. And then is calculate the wattage. And what that is, the voltage drop multiplied by the current draw of the LED at 0.02 amps, and then multiplied by a safe factor. The calculation results in, first, a 0.04 watt draw on the circuit, and then multiplied by the safe factor of 2, which gives us a wattage of 0.08 watts. And since resistors only come in 1/8 watt and 1/4 watt and 1/2 watt and above, an 1/8 watt resistor is 0.12. Okay, and therefore that is larger than the 0.08, so we are safe with a 1/8 watt resistor. In the following are practical tests. And in these practical tests, I tested a 100 ohm resistor, which is actually the calculation without a safe factor from Ohm's law. And that tested at 27 milliamps. And while the light came on and it was bright, after several tests, the LED burned out. And the reason is because the LED is 20 milliamps. So this is why we add in a safe factor. So after adding in the safe factor, the resistor comes out to 150 ohms. And this tests it out at 19.2 milliamps, which is below the 20 milliamps of the LED. I also tested this with a 220 ohm resistor, which is a typical resistor for an LED circuit with a 5 volt supply voltage. And that tested out at 13.7 milliamps. And while the light wasn't dim, it wasn't bright either. It was somewhere in between, of which can be adequate for most applications. The 5 other transistors in the security circuit require a calculation with at least 0.7 volts at the base, with a current gain calculation in the circuit. These transistors are called bipolar junction transistors and come in NPN and PNP types, while differing in where the semiconductor is doped during manufacturing. The NPN and PNP transistors work differently and are drawn differently on a schematic. The 5 similar transistors in this schematic are NPN BJT transistors. On this page, what we have is a symbol for NPN transistor and a diode transistor circuit. Preceding the diode is an R1 resistor, and this one happens to be the same resistance value as explained in the Ohm's law page, which is 150 ohms. And what we're going to do here is we're going to calculate the base resistance value that we need for the transistor. We must calculate the forward voltage drop of the transistor itself. And as you can see, this arrow is actually a diode inside the transistor. And this diode has a 0.7 voltage drop. So in the following calculations, what's going to be used is a BC547 transistor, which is the same transistor that's being used in the schematic. And according to the manufacturer's data sheet, a BC547 has a current gain, also known as HFE or beta, of between 110 and 200, while the typical current gain is 150. And therefore we will use 150. The LED that we'll be using is the same one from the Ohm's law calculations, of which we'll use the 150 resistor. All right, so what we first must calculate is the forward voltage drop. The supply voltage of 5 volts minus 0.7 for the forward voltage drop equals 4.3 volts. We can then calculate the R2 resistor needed at the base. And that calculation is the voltage from the previous calculation divided by the current at the collector divided by the HFE or beta divided by a safe factor. And the reason we need a safe factor is because if we didn't have a safe factor, what will happen is the transistor would only be in the active region. When we put the safe factor in there, the transistor changes from the active region to the completely saturated state, which we'll need for the draw on the LED. Now, if this was just a logic circuit, where all we need to do is have the transistor turn high or low, then the transistor could be in the active region, and still the logic would complete without having the transistor be completely saturated. Okay, so in this calculation, what we have here is a result of 1,323 ohms. And the following are practical tests for the base resistor requirements. As you can see, for a 10K resistor, the transistor is in the active region. The circuit is drawing 6 milliamps, and the LED is dim. At 5K, it's still in the active region, but it's drawing nearly twice as much current, while the LED is a little dim. And then when using the 2K resistor, the transistor is mostly saturated at 18.8 milliamps, and the LED is bright. As we get closer to the resistance calculation, at 1.5K, the transistor is almost completely saturated at 19 milliamps, and the LED is bright. When we get below the resistance calculation at 1K, the transistor is completely saturated at 19.2 milliamps, and the LED is bright. As we go lower with the resistance, higher with the current, at 500 resistance, there's no change. The transistor is still completely saturated at 19.2 milliamps. And then we drop down lower in the resistance value, and it's still completely saturated. Therefore, there's no need to go any lower with the resistance than 1K. So for this circuit, a 1K resistor is what will be used at the base of the resistor. The reason for these calculations is the collector to emitter current must be known to calculate how much current needs to flow from the base to emitter to allow the known amount of current to flow from the collector to emitter. The base to emitter current can be at least 50 to 400 times less than the collector to emitter current, while the typical transistor has a current gain of 100 times. The greater base current, the greater collector current, until the transistor becomes saturated, where the current gain levels out. Regarding the motion circuit, motion sensors contain either a single pole double throw switch and contacts that are normally open or normally closed, or a single pole single throw switch with a normally closed contact. Most modern motion detectors for security systems contain only a single pole single throw normally closed contact to prevent an intruder from cutting a wire while trying to disable the security system. I will discuss the motion sensor in more detail later in this video. Regarding inverter 1, since the motion sensor is wired as normally closed, and since there is a need to pull the SR latch circuit down low to set the alarm and lock out an intermittent motion sensor, there's a need for an inverter. Inverter 1 works with a secondary transistor to pull the circuit down low to switch the SR latch. Since current flows in the path of least resistance, when the motion sensor is closed, the secondary transistor is open while pulling the SR circuit up high in an unalarmed state. When the motion sensor becomes open, the circuit closes the secondary transistor and pulls the circuit down low to switch the SR latch and activate the alarm. Regarding the SR latch is enclosed in an IC chip with multiple NAND gates. These NOT AND gates produce high or low depending upon 4 different states on the NAND terminals. There are 2 different terminologies used to describe the NAND gate. High, high equals low. Low, low equals high. High, low equals high. Low, high equals high. And the other terminologies are 1 and zeros. After the motion sensor opens, the SR latch will lock out the motion sensors and activate inverter 2 to pull the 555 timer trigger circuit down low to start the timing. The SR latch will remain in this state until the capacitor in the RC circuit becomes over halfway charged and activates the comparator to reset the SR latch. While most simplified circuits on YouTube use momentary push buttons to pull down circuits for a second or two, if an IC chip is not separately protected, any extended pull down of an IC chip circuit can burn up the IC chip. Since the IC chip is separately powered, and as previously mentioned, current flows in the path of least resistance, if I used only one resistor before the IC chip, the current would flow from the separately powered IC chip and through the IC chip, rather than pulling down the supply voltage with lower resistance to ground. For safeguards, I used a 1K resistor for the VCC pull down and a 4.7K resistor in series to protect the IC chip. Regarding inverter 2 is activated by the SR latch and works in conjunction with a secondary transistor to pull the 555 timer trigger circuit down low to start the timer. The circuit remains pulled down low until the SR latch is reset by the comparator. The 555 timer gets the name from 3 internal resistors wired in series that form a 3-step voltage divider. The 555 timer can be wired in 2 ways: wiring the 555 chip as a monostable timer while separating the trigger supply from the RC charge circuit, or as an astable oscillating square wave generator dependent upon the trigger circuit being wired into an external voltage divider used mostly for charging and discharging the RC circuit. I wired the 555 timer as a monostable timer that works with inverter 2 to trigger and start the 555 timer, followed by an RC circuit to stop the timer. Regarding the RC circuit, in software engineering, an RC circuit is like adding a sleep function or delay timer function in a loop. The resistor value and capacitor value combination determines how much time it will take to charge the capacitor when the circuit is closed, and then how much time it will take to discharge the capacitor when the circuit opens. Regarding the comparator is in an IC chip which encapsulates multiple comparators. To auto-reset the SR latch to stop the alarm, and for the SR latch to again read the state of the motion sensor status, a comparator is used in conjunction with a voltage divider, and the same RC circuit used by the 555 timer. The comparator then activates a transistor to pull the circuit down low and reset the SR latch. Now I first chose an LM393 comparator. However, the LM393 was unresponsive. I then chose the LM358 op-amp for the comparator, and everything worked out fine. Just like the experience with testing Ohm's law with the diode, and the diode with transistor, and discovering the SR latch IC burning up without a protective resistor, the comparator experience is another example where practical experience is more worthy than conjecture, speculation, and hearsay. The following is a picture of a commercial security system. At the top, there is a Concord 4 main circuit. And below it is a power supply with a battery backup. If you look closely at the top board, in the Concord 4, what we have is at the top and bottom of the board are the zones, and this is a 4-zone board. However, it is only using part of one zone in the schematic. It appears there's only one zone. However, you can tie multiple devices together in series, such as multiple motion detectors. So on the right side of the board is the power input to the board, and then on the left side of the board is the keypad. Now, in the circuit that I designed, rather than using a keypad, there's only a couple of manual switches. And if these switches are located in a discrete location, then it should be adequate. Now, regarding the lower board, which is the power supply and the battery backup, for the security system that I'm using, to power the main circuit, I am using a 120 volt AC to 16 volt AC transformer with an auxiliary power supply circuit board supporting a 12 volt battery backup. The external circuit board includes 4 diodes forming a full bridge rectifier to convert AC to DC, while including a linear voltage regulator to step down 16 volts to 12 volts while dissipating the 4 volts through a heatsink. To step down 12 volts to 5 volts, since the voltage drop is more than 4 volts, a linear regulator of this type would become even more inefficient and require a more substantial heatsink. Therefore, I chose a more efficient 12 volt to 5 volt switching regulator. The following breadboard incorporates a 12 volt to 5 volt switching regulator, also known as a buck converter. While a switching regulator can cause frequency interference with other frequency sensitive devices, since there are no other frequencies near the panel box, a switching regulator is adequate. Since there is already plenty of information regarding buck converters on the internet, I will briefly summarize by stating most buck converters center around a 2576 or 2596 IC chip. The only difference between the chips is the switching frequency of the chip and the size of supporting components required by the chip. The following is the PCB-ready schematic and is similar to the previously shown schematic with most of the addition of a buck converter at the top. Also notice how the external components such as the horn, bypass switches, and normally closed motion contact were removed and relegated to a 5-pin header input. While the logic in the previous schematic is fundamentally correct and will be demoed later in this video, since the 555 timer trigger is very sensitive and will trigger if the voltage drops below 2 volts for a fraction of a second, and will even trigger by simply placing a voltmeter on the trigger lead, to prevent false triggers after extended runtimes, I redesigned the trigger circuit by separating the transistor pull-down supply from the trigger supply while utilizing different resistor values and capacitor values to only pulse the trigger. Regarding the breadboard prototype demo, I'd like to first discuss this motion sensor in just a little more detail. The motion sensor I am using is a high-quality Dual-Tech motion sensor with passive infrared and microwave. The infrared senses heat signature changes in the room, and because it depends on movement across the infrared sensor beam, sometimes you can walk straight up to an infrared sensor without it activating. Conversely, the microwave sensor echoes microwave signals off of objects in the room, or even through a window. And because the microwave sensor calculates the time it takes an echoed microwave signal to return, if a person walks straight up by moving closer, the microwave sensor can detect their movement and then activate the alarm. The final part of this video will be the breadboard prototype demo. I want to preface the final part of this video with the sequence of events in the video. What you should focus on first is the motion sensor, where I will activate the motion sensor. And then the red LED will light, followed by a yellow line on the oscilloscope rising. That represents the capacitor charging. And then what you'll see is the pink line representing the comparator suddenly jump up, followed by the yellow line continuing to gradually rise until it just passes the pink line. When that happens, both lines on the oscilloscope will collapse, representing the security circuit auto resetting. If you like this YouTube video, or just learned something in the video, please click on like below this video on the YouTube page. Thank you.